This is section 9.4, comparisons of series. There are two different tests in this series. One is both of them are easy compared to, say, the integral test. Okay, they're about the same level of difficulty as the nth term test for divergence, but the easy one, the good one, is only as good as your skill in taking limits. Okay. All right, so let's start this. There are two tests in here, the direct comparison test, which is useful if you have something easy to compare to. If you can't think of anything easy, then the limit comparison test. And in fact, it's probably better to just use the limit comparison test whenever you can, and the other tests when the other tests are just obvious. Okay. All right, so here, direct comparison test. So this is a geometric series that we know about, and this is not a geometric series. Okay, so it looks like it, but it's not. Right. So you can't use a geometric series test on this. You would have to do some other test. Here's a P series, right? So that's a P series that we can do a P series test. And this is not a P series. That little +1 just ruins things for the P series test. Okay. So what does it mean though? However, you could use some other test. All right. So the direct comparison test is useful for looking at problems that are similar to other problems. Like, so this P series, this is not P series, however, it's close to a P series, so maybe it's something to compare to. All right, so let's look at a direct comparison test. Now, this theorem, this big idea theorem, is going to come up frequently in a multiple choice scenario, right? So here we're saying that one series is smaller than another series for all values of n. And this all value in n is kind of loose. It could be like n greater than or equal to 4. Right? So there's a beginning point, some beginning point for n. Then from then on, this is true. Okay. So here, if b and n converges, so the bigger one converges, then the smaller one converges. If the smaller one diverges, then the bigger one diverges. All right. So determine the convergence of this series. Now looking at this looks like the geometric series 1/3 to the n. And, right, which is a convergent geometric series because r is 1/3. And here, this fraction is smaller than this fraction. Remember, whenever you add anything to the denominator of a fraction, it makes it smaller. So if this is the regular fraction and you add 2 to here, it makes this fraction smaller. So we have the condition where a sub n is smaller than b sub n. So by the direct comparison test, this series converges. I thought I said diverges. That was my pause. I misread my own thing. All right. Anyways. All right, let's look at this one. Determine the convergence divergence of this series. Now, this looks like this one, right? Which is a divergent P series. But this series is smaller than that one because you're adding 2, it makes it smaller. Being smaller than a divergent series really doesn't help, right? This is no good. Being smaller than a divergent series doesn't prove anything. So what do we do then? Well, we compare it to 1/n. Now, if I were you, I would say, well, how would I think to compare it to 1/n? You're right. So this is the direct comparison test is not a good test for this series. Okay, but we'll just go through the ropes and use it anyways. So this is now we know this is a divergent harmonic series, and we can compare these terms side by side. And look at all the work I got to do this, right? N to 1/n to 1/2 plus n. So this is my n, right? So I'm going to start at n equals 3. Yeah. 1/3, 1 plus 2, 1/2 plus root 3. Actually, this is still bigger, I think. All right, 4, 1/4. Now they're the same. Plug in 5. So 1/5 is 0.2. This is 0.225. So now this one's bigger, right? Remember, we want to be bigger than the divergent series, or equal to. So here it was equal, this was the other way. All right. So 1/6 is 0.16. This is 0.236. So what's happening here is that these terms are now bigger than 1/n. So the terms for 1/2 plus root n are bigger than the terms for 1/n starting at n equals 5. All right. So if for n is greater than or equal to 4, this 1/n, the series we know about, are smaller than or less than or equal to the series where we're asking the question about, right? So the smaller one diverges, so that means the bigger one diverges, okay? So So by the direct comparison test, this series diverges. But I agree, this was a royal pain just to do this. But a better test is coming. Alright, if this is true, right? If this comparison is true, and we know it, right? The smaller series if the smaller series diverges, then the larger series diverges. If the larger series converges, then the smaller series converges. And this is a big idea. This is a big picture idea for all series. So this is going to come up in multiple choice situations, right? Where they're going to ask a situation, say, why, if this series converges, why do we know the other series converges? And this is the big idea. Alright, but example 2, the one you just solved, the 1 over 2 plus root n, is a motivator to find a different test because that comparison was a pain. Alright, so let's do some other ones. So this is the good one. This is your new favorite test. You know, that's after, well, it does require that you have mastered the geometric series test, the p-series test, and n-term test for divergence. But these were easy, right? The geometric series test is easy. All you gotta do is say, okay, well, some of us still have difficulty recognizing that geometric series, right? Because that can be tricky because they will write it as 1 over 3 to the n or 1/3 to the n power, right? You got to recognize that those two are the same. P-series tests, they're usually pretty straightforward. N-term test for divergence, that one requires that you know how to take limits, and so does this though, right? You have to be able to take limits. Alright, so this is a nice little review of how to take limits as n goes to infinity. Alright, let's continue. So we're going to use the limit comparison test to prove a general harmonic series divergence. Alright, so this is the regular harmonic series, 1 over n. And so we're going to call this C. I know on the little theorem there was A and B, but there's A and B already here, so I'm going to call them C and D. So C is the known harmonic series, so D is the generic harmonic series. All right, so we do the comparison. I'm putting C on top and D on the bottom, and it doesn't matter which one you put on top, right? You're still taking the limit as n goes to infinity, and if it doesn't go to a certain number, then it's toast anyways. All right, so here, so I do some algebra, right? Do some algebra. The 1 over n stands up on the bottom. Then you flip this, so that means it ends up on top, and you take the limit as n goes to infinity, so that equals a. And remember, a is a positive number, and that's what the limit comparison test requires. It's a positive number. Now we know that. Okay, sorry. All right. The limit comparison test says once you've taken the limit, that means the two series behave the same way. We know that the harmonic series diverges. That means this generic harmonic series also diverges. They behave the same way. If one diverges, the other diverges. If one converges, the other converges. This one, we had a divergent harmonic series. We have just shown, because it goes to a positive number, because the limit of the comparison is a positive number, the limit of the ratio of the two series is a positive number, they both diverge. Alright, since A is greater than 0, because of the given, by the limit comparison test, they behave the same. Since we know one diverges, then the other diverges. Alright, quick comparison to P-series. So here, this is 1 over 3n squared, so we're basically going to ignore the negative 4n plus 5, right? In fact, when we compare, we don't even ignore the coefficient. We only care about the highest exponent of the variable, right? Since this converges by the P-series test, then this will also converge, right? And you can use the comparison test to prove it. This is n to the 1/2. We know n to the 1/2 diverges by the P-series test because P is less than 1. So that means this diverges. Right? Both diverge. Here, you want to look at both exponents, numerator and denominator. That's going to give me n to the 3rd in the denominator. So this one, the 1 over n to the 3rd in denominator, the n to the 3rd in denominator, that's going to converge because by the P-series test. So that means the original series over here is going to converge. Alright, what about something as complicated looking as this, right? So look at just the exponents on these. So square root can be raised n to the 1/2, so that's 1 over n to the 3/2 when we reduce that. So you're going to compare it to 1 over n to the 3/2. And that series also converges because P is 3/2, which is greater than 1. Now, so AN in our example is what? The original function, or original series rather, and BN is the series we want to compare it to. Do some algebra here, so the numerator stays the same, but the denominator flips, right? right? That's that flip version. So you're going to multiply these two, and you're going to get n squared, right? N to the half times n to the 3 halves. Half plus 3 halves is 2. That's where that n squared comes from. Now take the limit as n goes to infinity, and that's going to 1. Remember, if the degrees are the same, you just look at the coefficients. So this is a good practice for that if you're still rusty on limits there. All right. And if this doesn't come up with a number, you chose the wrong series, okay? And you don't want it to be 0 either, right? You don't want to compare, have it turn out to be 0. 0 is inconclusive, right? You want it to be positive, and you want it to be finite. We want it to be a regular number. All right. All right. So we had this is a convergent P series, and by the limit of the ratio is positive, which was 1. By the limit comparison test, the original series also converges. All right, so this is just restating what I said in the last slide. Okay, this is just doing it again. All right, so let's look at this one. Oh, this is as complicated as you can get, right? Here, 2 to the n over n squared. What does this do? Let's see, 2 to the n, that's going to diverge by the nth term test for divergence, because 2 to the n overpowers n squared. That's going to shoot out to infinity. So by the nth term test for divergence, that is not 0. Okay, so compare this fancy series with this simpler series that we know diverges. All right, do some algebra here. So in other words, you keep the numerator as is and just flip the denominator. By the way, if you want to go jump straight to this just by flipping the denominator to begin with, that is okay. You can do that. You don't have to take this step. This is a really cumbersome step. All right, but here, look what happens to the 2 to the n. They reduce, they go away, right? And you have n times n squared is n cubed, so you got 4n cubed under n cubed, so the limit is 1/4. Okay, and we know this series, the 2 to the n over n squared, diverges by the n term test for divergence. So this, the original series, also diverges, right? Because the limit was 1/4. By the limit comparison test, the series diverges. So in this video, there were 2 more tests for convergence and divergence, right? Direct comparison test. Use this test when the comparison is easy or obvious. Okay. And you know what? You will only be required to use this test when in the directions it tells you to use this test. Or they'll ask the question of, by the direct comparison test, can you say that this is convergence or divergence? And you can say whether it's true, false, it's not a good test, it's a bad test, whatever. All right. The limit comparison test, this is the most useful and reliable test. This is the test that students were using when it was not part of the AP curriculum. But because it's mathematically good, the AP people had to accept that as a reason. And they finally added this test to the AP curriculum. All right. So this is the good test. This is the one you're going to be most useful and reliable. But it does assume that you know the P-series test, geometric series test, and the nth term test for divergence. Those 3 are your go-to before you go to the limit comparison test. Okay? All right, that's it.